Yeah, so this talk is mostly going to be kind of an overview, maybe like a motivation for taking some ideas which are maybe viewed as a little bit more esoteric, a little less applied math, and applying them within machine learning. And so in particular, we're going to look at this problem of like local biases, imparting local biases within representation learning algorithms. And in particular, we're going to focus on graph representation learning algorithms. So it will become clear later why graph representation learning. But the hope would be that this general theme of taking these concepts from sheaf theory and even higher into category theory, this should extend to not just graph representation learning, although many problems in machine learning due to the discrete nature of the field can kind of be cast within this graph learning framework. So anyways, so I'm going to, oops, there we go. So I'll give it a little bit of motivation. We're going to look at two graph representation learning problems as kind of starting points to just get a feel for how these local biases are being introduced within these problems, what kind of not necessarily state of the art, but machine learning algorithms like this deep walk node embedding framework and graph convolutional neural networks. We'll just get kind of a feel for them and kind of fix some notation that later on, after we talk about sheaves and cellular sheaves, we'll then show how we might be able to generalize these types of algorithms. And so in the application section, I'll just give a brief overview of some of the work that's going on in this area. And I'm happy to answer more specific questions at the end. I'm going to turn my fan on very quickly here. That makes too much noise. So representation learning, it's really just a ubiquitous notion within machine learning. And broadly, we just are looking for some tractable representation of some complex space. So we're going to take samples from a space. We want to encode them in a manner that is both like tractable and also retains some structure in this data space that would allow us to later on, or for some downstream purposes, for example, classify our samples. And so we can give a slightly more formal definition. I'm not calling this a formal definition, but it would at least give us something to get a handle on a little bit better. So if we view our data space as some like topological like union of sets, and we're going to define our representation is just a map that takes us from this data space into some representation space. And if we have some sort of relationship that's given by maybe a map G, we would like this relationship to be recoverable within our representation space in a way that's kind of commutative in a sense. So you can see the category theory leaking in here. And I'm not saying this is a formal definition, but it is maybe something to grasp onto from an intuitive standpoint. And so typically we don't actually know what these G maps are or should be. But one way one can kind of bootstrap these G maps is by looking or imparting some sort of local smoothness. So like imparting an inductive bias, which says that if things are in some sense nearby in our original space, in our input data space, we want them to end up nearby in our representation space. So let's look at a couple examples. As I said, we're gonna look at deep walk, which is a node embedding algorithm. So if we have a graph where now V is our set of vertices, broadly we're looking to map these vertices into just some vector space, which we would hope it kind of encodes the semantics of the underlying graph. So to actually perform this node embedding, what deep walk does is generates a corpus of kind of node visitations where we we start random walks from each vertex in V, and then just keep track of all of the nodes that were visited along this random walk. Deep walk then uses the skip-gram with negative sampling embedding framework, which is what node-to-vec uses. And really, deep walk is just kind of a graph version of node-to-vec in some way. And the result of this process is that the learned embeddings are assigned similar, or nodes that are nearby in this random walk sense are assigned similar vectors in our representation space. And so we can break this down a little bit further to really see what this like local inductive bias is. And so it's fairly well known at this point that this skip-gram with negative sampling approach to embedding is implicitly performing matrix factorization on like the pointwise mutual information of each like word or node in this case, given its context. And so we can write down a similar graph-theoretic form of what matrix is being factorized. And we see here this is kind of like the probability after t steps, or within t steps of passing between u and v from u, and also passing between u and v from v. So the real point to take away here is that we have this transition matrix which shows up, which is encoding some sort of like flat representation in the sense that any path between nodes u and v is treated equivalently. But this could break down in practice if our edges are in some sense typed, or if a walk down path R1 versus path R2 have drastically different semantics. So just keep this in mind as maybe a motivating question or potential problem. The other the other algorithm I want to talk about is graph neural networks, which is weird to call them an algorithm, but the other idea I want to talk about, maybe graph neural networks. So one can view graph neural networks from this very general message passing neural network framework, which takes, so if we're given signals defined on a graph, so graph neural networks are performing some sort of like graph signal processing task. We're given signals x, v on each node of our graph. What this message passing neural network framework does is iteratively query nodes in the neighborhood of v, and then aggregate, message pass with those nodes. So given the representations at v and u, we're going to perform some sort of message passing operation in this local neighborhood. And then we're going to aggregate these representations, defining our new representation at node v based on this message passing and aggregating operations. There are a number of different ways to implement this message passing neural network framework. I mostly laid it out because it's easy to see kind of where this locality bias comes from. One of the most popular ways to implement this message passing framework is using graph convolutional neural networks, which employ the graph Laplacian, which is this L tilde here. It's actually the normalized graph Laplacian, which performs this message passing operation on the network. So this is a completely linear algebraic operation, and this I minus, or the identity minus the graph Laplacian performs diffusion of our signals at each node amongst neighbors. So the important thing to note here is that if we just were to repeatedly apply this diffusion operator on some channel of our entire signal across the nodes, so the channel I of our entire signal across the nodes, the quadratic form would go to 0. And so what this means is we're minimizing the Dirichlet energy. So we're minimizing, the energy of this form, meaning that we're pushing the representations of nodes to align with each other. And basically we're learning some sort of constant function if we were to simply fix our weight matrices and just apply or just concatenate increasingly make our graph convolutional neural network longer or deeper in some sense. So as I said, these features will become constant. They'll minimize the Dirichlet energy, which means they'll approach the kernel of the graph Laplacian. So the graph Laplacian again has a number of different interpretations or ways to define it. Maybe just keep that in the back of your mind. And so again, maybe a motivating question for graph convolutional neural networks will be: is there a way to derive something that looks like a graph convolutional neural network, but whose message passing is, maybe is able to avoid these trivial or flat constant functions? So another motivating question. Okay, so now I'm going to move into sheaves, just a discussion of sheaves from a very high level. And so there are a number of different levels which one could introduce or give a definition for sheaves, and especially cellular sheaves. I've ordered these by the categorical primordial ooze that's needed to understand them. And so typically when I introduce sheaf learning or sheaf neural networks, I'll typically start from level 1 and work my way up, as in the machine learning area, this abstraction of graph signal processing is very familiar to a lot of machine learning folks. But because this is a math seminar, I feel like I can actually start at the hairier category theory level, so level 4, and work our way down. And so the nice part about starting at the categorical definition of a sheaf and working down is it's going to be very clear which assumptions we're making in order to operationalize these concepts, or in order to implement some of these ideas, which are implied by the definition of sheaves. Okay, sorry about that. So this categorical definition is going to come from Justin Curry's thesis. It's a very good dissertation, very readable. And if you want to kind of read through these definitions in a little bit more detail and clarity, I would recommend just reading through his thesis. It's really good. Okay. So what is a sheaf? We're going to take some topological space X and assume we have some open cover of X. We're going to define the nerve of this cover. We're going to assume we can take the nerve of this cover and define this iota functor, which is going to take us from the opposite category of the nerve, viewed as a category, into the category of open sets on X, or the opposite category. Okay, so this is just going to give us kind of a way to move from open sets into more of a cellular or nerve-like definition. So a pre-sheaf valued in what I'm going to call the data category D is just a contravariate functor from the category of open sets on X to D. We also have the morphisms, which are restriction maps, which map us between if there's a set inclusion U into V in our original category. We're going to have restriction maps which restrict from V down to U, or the representation of V down to U. Okay, this pre-sheaf then is a sheaf if we have kind of this, if it factors through this the limit, if it's a limit object with respect to this kind of indexing category given by the nerve. So if one understands limits in the categorical sense, this is a perfectly fine definition of a sheaf. But for my use cases, I would like to know a little bit more, or like a bit more of a specific definition, which would give an indication as to how one might actually get a handle on computing this object. So this limit has to, in some sense, sit inside the product of the vertices of this nerve. So we can equivalently define a sheaf as the equalizer of this diagram here. So what is the diagram doing? Well, we're going to take our vertices on the nerve. We're going to look at their we're going to look at the product of the representations, and then we're going to map this this product. We're going to project out of this product onto intersections, and these intersections are going to be in some sense oriented. So this kind of projection onto intersections is going to be adjudicated by this F minus and F plus maps. And broadly, we're saying we want a representation which aligns on set intersections. I find it slightly easier to interpret this definition by just revisiting the definition of an equalizer. So if we have like a set function, if we just replace this product of our vertex representations by A and this intersection product by B, you know, a regular definition of the equalizers is available. If A is constant at B, or if F plus is constant at B, we recover something which looks like a fiber. And most importantly for our use cases, if we're working over vector spaces, this equalizer becomes semi-computable in the linear algebraic sense. So the kernel, or sorry, the equalizer of these two maps is going to take the difference between them and then look for the kernel. And so we're going to actually give this difference between these two maps a name. We call it the co-boundary. And so we're going to be hunting for the kernel of the co-boundary. So just to recap the Sheaves definition, the categorical definition, we have this assignment of data to a space, which is a very important kind of intuitive abstraction. This assignment of data is kind of determined by the product of the assignments on the vertices of this underlying nerve. We can move towards a computable sheaf. We can compute a sheaf if we view it as an equalizer of this kind of oriented intersection structure. And in particular, when we're working when our data space is the category of vector spaces, this becomes kind of a linear algebraic problem. Okay, so we're going to move on to cellular sheaves, which, so up to this point, I've left this, our kind of, our original space, our topological space, I've left it more or less unchanged from the definition of sheaves. But in practice, like knowing what this open set structure is difficult. It's not given to you a priori. But if we're working over graphs, we do have a natural way to encode graphs as like provide them with this open set structure. And so one way we can do this is to endow these graphs with the Alexandrov topology, which basically we have these open sets emanating from each node, and their intersection is going to be defined over the edges. So we have, again, our product space now on a graph is going to be our representations at each node. And our equivalently, this like intersection, this product of intersections is going to be representations on edges. Okay, so I want to keep in mind the broader goal here, which is we want to use this kind of sheaf-theoretic framework as a model for representation learning. So to define a sheaf, we require a topological space. Within machine learning, this is usually given to us. And we just saw on the last slide how if we're given a graph, there's a very natural way to encode the open sets on the graph. This is not the only way, of course, but there, we have at least a way more or less you might call it a canonical way if we're just given a graph. We need some sort of like cover, which is generally ignored within machine learning. Again, this is something to keep in mind if we're moving away from this kind of canonical open set structure in the Alexandrov topology. To define a sheaf, we require this data category. So like the data we're going to assign to our underlying space. Within machine learning, this is almost always the category of vector spaces. So in terms of generalizing these ideas or kind of further playing around within the categorical ooze, if you will, choosing different data categories is kind of an interesting avenue for future work. And finally, we have these morphisms, which come from this functor given by the restriction maps. And within machine learning, this is almost always ignored or assumed to not exist, assumed to be trivial. And so what this provides us is kind of a framework for like what's already here and what we can generalize using this sheaf-theoretic framework. Okay, so let's drop all the way down to just defining what a sheaf on a graph looks like. So if we have a graph, we're given a graph G. A cellular sheaf on a graph is an assignment of a vector space to each vertex, a vector space for each edge, and then these restriction maps, which are going to be now linear maps because we're working in the category of vector spaces for each incident vertex edge pair. And so cartoonishly, you might draw it like this, where you have these vector spaces sitting over each node, and then some linear map or matrix which transforms each incident vertex edge pair onto this edge vector space. And so if you recall from our categorical definition of the sheaf, we need some notion of this product over vertices, which we can define pretty easily as the space of zero cochains, C0. And similarly, we can define this intersection product space is the space of one cochains. And if we're working in the category of vector spaces, their data category, this is really like this product is a concatenation of vectors. So we're going to take all of our zero cochains on each node, and we're just going to order that properly into one long vector is what an element of this product space is going to, in some sense, look like. This co-boundary map has a nice definition in the sense that for a given edge E, the co-boundary computes are kind of positively oriented. Take the zero cochain at V mapping onto edge E through this restriction map, which restricts to our edge, minus the oppositely oriented U onto E. So as we saw before, or as we noted before, we're going to be hunting for kind of the kernel of this co-boundary. And so the space of globally consistent, so that basically this space defined by the sheaf, globally consistent assignments of data to our vertices of the graph is the kernel of this co-boundary operator, which sits within inside this product space, as we saw earlier. So note that this co-boundary map takes signals or zero cochains onto one cochains. One might then ask, and maybe it's a bit of a leap, but you might ask whether you can do anything with this operator in a similar sense that we have this like incidence or co-boundary matrix for graphs, which forms the graph Laplacian. You could ask whether this co-boundary matrix for cellular sheaves forms something like a sheaf Laplacian. And of course, the answer is yes. Excuse me. So Jacob Hansen and Rob Grice have done a lot of great work on detailing the kind of spectral properties of cellular sheaves, viewed through primarily the sheaf Laplacian, which would be this kind of inner product of the coboundary matrix. And again, just like the graph Laplacian, there are a number of different ways to define this, but hopefully it's pretty clear from this slide that this at least morally looks like the graph Laplacian. And in particular, this last line, where we're taking this quadratic form of zero cochains with the sheaf Laplacian, we end up with something that kind of looks like the Dirichlet energy from our original quadratic form over the graph Laplacian. But this time we're taking kind of like the L2 difference between these signals on, or these zero cochains on V and U across all of our edges. So this gives us a measure of like how consistent our assignment of data is. And of course, if this is equal to 0, we know that this cochain must sit within the space of closed sections. As a final note, we can recover the graph Laplacian pretty easily within the sheaf-theoretic language, meaning that in some sense it is a proper generalization of kind of a spectral graph theory, at least in the co-homological sense. If we take our vector spaces over our nodes to be just a real number, just the one-dimensional reals, and choose our restriction maps such that they give us back a weighted adjacency matrix from our. So if we have a graph, it's a weighted adjacency matrix, we can very easily find what these restriction maps have to be, which would give us this weighted graph structure. If we find those, then we have basically a cellular sheaf, which is equivalent to the graph, or sorry, a sheaf Laplacian, which is equivalent to the graph Laplacian. But also the takeaway from this slide is the graph Laplacian, a very simplistic form of the sheaf Laplacian. Okay, so how do we actually use this in practice? How is this being used in practice? So if we recall our first kind of motivating problem, we were looking at graph embedding. And one of the issues was if our edges were typed, this kind of locality constraint might throw off our representations in some sense, because we're always looking to push things which live in our random walk neighborhood that are nearby in this random walk sense, to have representations that are also nearby in our representation space. Knowledge graphs are an example application where where the type of the edge is actually important to the semantics of the knowledge contained within it. So a knowledge graph is basically just, we can define it somewhat rigorously as having a definition of some schema, which would be like this kind of multi-graph structure down here, which defines our typing on the knowledge graph. And then we're going to view some graph morphism from a graph, just some graph structure, into this schema, meaning that we're going to basically assign a type to all of these nodes in the network. And here I've labeled these nodes with their types. But if we were to perform just a simplistic random walk on this knowledge graph and try to learn embeddings, we would end up learning representations of Julia and movie or Fargo, representations of people and movies which are nearby to each other, which may not be desirable. There may actually be a huge difference between people and movies in our representation space. And so the issue is that we have this typing schema, which means that not all paths in our local neighborhood should be treated equivalently. So we're kind of breaking an underlying homophily assumption. And so in some of our more recent work, we've shown that you can frame this knowledge graph embedding problem, so if we want to learn vectorized representations of our entities, we can frame this as like hunting for a sheaf, which we're calling a knowledge sheaf. And so the general recipe for this is to, we're going to learn this using some sort of contrastive learning approach where we, for our actual, node, edge, node triplets, we're going to look for representations, so zero cochains, and restriction maps at the same time, which minimize this quadratic form or minimize some notion of consistency across the resulting cellular sheaf structure. And it turns out that many of the most popular knowledge graph embedding methods which already exist are doing some form of this sheaf. They're performing sheaf learning, albeit unbeknownst to probably most of the authors. So this is interesting in the sense that kind of the community, the machine learning community, has more or less derived this cellular sheaf structure on their own. And it is a very natural way to solve this typed graph embedding problem. But when we reinterpret this knowledge graph embedding task within this cellular sheaf framework, it gives us a little bit more power, especially in the form of making full use of the sheaf Laplacian to, for example, define boundary value problems. So if we're trying to perform a query which has multiple hops in it, so instead of just querying like who is Julia's friend or who's the friend of Julia, we're going to say like what is Julia's friend's favorite movie, for example. And so to perform this multi-hop query, we're going to basically compute a new sheaf which quotients out all of these intermediate nodes and solves this boundary value problem by fixing Julia and fixing all of the relations between Julia and this unknown end node. And in the L2 sense, recovering what like the best harmonic extension on this new smaller sheaf should be. So there's more details in our paper, but this is one way you can use this kind of cellular sheaf framework to kind of make inroads in areas where maybe people are already using this cellular sheaf, these ideas from cellular sheaf theory and these ideas of local and global consistency. The other way the other location cellular sheafs have been showing up is as abstractions or generalizations of graph convolutional neural networks. So in our original definition of graph convolutional neural networks, they seek to learn basically representations, so taking signals on a graph and learning representations of these signals, so latent representations at each node, which allow you to, for example, classify the nodes into distinct categories. We can define a similar problem where if we're given sheaf-valued signals, so we're given cochains and some restriction maps, we could pass this through something that looks like a graph convolutional neural network. It has the same form in that we're going to use the Laplacian to diffuse information or to message path information across the network. But now this Laplacian is actually the sheaf Laplacian. So we're diffusing with respect to the constraints imposed by the restriction map, so the constraints of the sheaf. And so just as a comparison of these two methods within this kind of notation, which I've built up at the beginning, graph convolutional neural networks, the main takeaway here is the Dirichlet energy, which we're implicitly minimizing by stacking these layers, both within graph convolutional neural networks and sheaf convolutional neural networks is being minimized. But note that we have this extra value of these restriction maps in the sheaf case, which would allow us to learn of non-smooth representations or non-flat representations, in that we're not requiring xv and xu to be equivalent as we are in the graph convolutional neural network case. And so the benefits of this sheaf convolutional structure is that if we have, again, some sort of like typed graph or a heterogeneous graph, you might call it, the sheaf diffusion process is just much more expressive and doesn't push the representations towards these potentially pathological locations within this representation space that would require things that are nearby in the random walk graph sense to be nearby in our representation space. So for example, we showed in our original sheaf neural networks paper that sheaf convolutional neural networks are, if you have like a signed graph where the class of a vertex is dependent on the sign or the typing on the edge, you'll get basically random performance from graph convolutional neural networks, but you actually can learn this within a sheaf. And in some very good follow-up work by Christian Bodnar et al., they showed that indeed this kind of heterophilic advantage of sheaf convolutional neural networks does play out in the real world as well, where they've listed these data sets, the performance on these data sets, according to the level of homophily. So like core is a very homophilous network. So the labels that should be assigned to the correct classification on the core data set are very homophilous versus some of these earlier data sets. So just to wrap up the summary, hopefully you can kind of see how these sheaf-theoretic ideas, and especially sheaves as this like equalizer object, provides a nice like natural objective for these kind of representational constraint learning problems, constrained representation learning problems. This model can also clarify, the sheaf model can also clarify a lot of the assumptions that are being made within graph signal processing or graph representation learning. And understanding of these assumptions also allows for one to more readily generalize these algorithms to maybe some more esoteric data types. We saw a little bit how sheaf cohomology provides kind of a computable version of this objective, of this equalizer objective. And these things are already being used. We can already implement a lot of these ideas because at least if our data category is category vector spaces, as I said before, we have this kind of implementable linear algebraic form, which allows us to search for globally consistent assignments of data. So with that, I'll open it to questions. It is my birthday, so you have to be nice to me with these questions. But otherwise, yeah, I'm happy to answer any questions.